Evolution is a race between predator and prey. And more often than not, speed means survival.
Being fast is the name of the game.
Prey becomes faster, predator becomes faster.
How could fish fly through the water at nearly 70 miles an hour? How could T-Rex evolve to outpace the fastest human? And what happens when we push nature beyond the natural limits? Buckle up. Speed kills right now on Evolve. In the blinding heat of the Savannah sun, the predator spots its prey. Within 3 seconds, it's reached 60 miles an hour. As it closes in, it hits maximum speed, 70 miles an hour. The cheetah is the fastest animal on Earth, and its speed has just one purpose: to kill.
Speed is sometimes the difference between life and death. Speed is what allows prey to escape their predators, or it allows predators to catch their prey, and can mean the difference between survival and extinction.
Today, speed gives the cheetah the highest predatory success rate on the Savannah. A lone lion catches its prey in 1 of 6 hunts. A full 50% of the time a cheetah hunts, it kills.
Cheetahs are the perfectly adapted animal for running. Their bodies have evolved literally from the tip of their nose down to their tail to help them run faster.
A wide range of factors affect an animal's speed, environment, body type, predation, and more. And every one of those factors has come together in the evolution of the cheetah to create the ultimate sprinting machine. The head, smallest relative size of any cat, its aerodynamic design cuts through wind like a bullet. The collarbone, reduced and free-floating, it's like a tiny axle for quick, tight turns. A massive chest holding a huge heart and lungs to pump fuel to the muscles. Legs, long and light, with extended Achilles tendons for superior shock absorption. Claws, non-retractable like a dog's, they dig into the earth with every stride, providing traction. And the heavy tail that helps the cheetah steer.
It's awfully hard to keep your balance when you're chasing a gazelle who's evolved to turn directions in midair. So cheetahs use their tails literally like a rudder on a boat, and if they turn it, it allows them to make much sharper turns. Speed is really generated from strides. Once every foot has touched the ground once. Any running animal, to increase their speed, needs to increase its stride length or its stride rate. And cheetahs have managed to increase both of those.
Scientists studying humans have shown that runners need powerful leg muscles for long strides. These muscles bring the leg down hard, launching the runner into the air for a long leap-like stride. But the cheetah's legs are thin and fragile. So how do they achieve long strides?
Most people assume that cheetah's speed is generated from their legs. They must have really powerful legs. It's actually on their spine. About 60% of a cheetah's muscle mass is packed onto its spine. So if you combine that with those elongated legs, you get an animal who has an average of about a 23-foot stride length. And that's incredible.
Flexing its spine like a coiled spring, the cheetah's body flies out, airborne for a distance more than 5 times its length. At a top speed of 4 strides per second, the cheetah can cover an entire football field in a fraction over 3 seconds. The cheetah's speed is the secret to its survival, an asset that evolved sometime between 3 and 5 million years ago. When cheetahs first emerged, they lived alongside massive predators like Smilodon. The 800-pound saber-tooth was twice the length and up to 8 times the weight of a cheetah. A top predator, Smilodon had the market for slow-moving, massive prey locked up. But there was room for a fast predator, and the cheetah and its ancestors were fast. It could run after the prey a big predator would never catch. Speed ensured the cheetah's survival. But there were trade-offs.
The cost is that you can't do what other cats can do. You can't fight.
The cheetah's light weight makes it an easy target for larger predators when it's young and slow. Up to 90% of each generation of cubs are killed by lions, wild dogs, even eagles. And even though the cheetah takes down prey more often than any other savanna predator, half of everything it catches is stolen away by slower, more ferocious animals, like the hyena. Fortunately for the cheetah, there's always another meal just a 70-mile-an-hour sprint away. The cheetah is the fastest animal on land. In the air, the peregrine falcon can hit a cheetah-like 68 miles an hour flying straight. In a long dead drop, as fast as 270 miles an hour. And under the waves swims the cheetah of the sea, the sailfish.
Sailfish are thought to be capable of achieving speeds in excess of 60 miles an hour.
Sailfish roam the warm waters of all 5 oceans. Deadly predators that eat their marlin cousins, tuna and more, knocking down prey with their upturned bill. Even leaping out of the water to take down flying fish. Up to 10 feet long, they can weigh over 100 pounds, swim faster than most sport boats, and are a legendary and elusive prize for fishermen.
What do you think it is?
Fish.
Sailfish can pull out a football field of line, 300 feet in 3 seconds. How do they generate this incredible speed?
Now, while most fishes swim by putting sinuous waves down their body, sailfish don't. They tend to keep the body fairly straight.
They are so fast that they have been nearly impossible to study, and very little is known about their speedy lives. Fast cheetah, falcons, and sailfish are all descended from the same root, the evolution, over 500 million years ago, of fish with backbones, the first vertebrates ever on Earth.
In many ways, we're all fish. The first vertebrates were fish. Fish are the most diverse group of vertebrates that still are alive today, and everything else is just a variation on a fish.
Vassar College biologist John Long traces the birth of animal speed to the Cambrian explosion, when animals evolved into the first predators, and rapid changes followed, among them the need for speed.
As soon as you have predators, you have prey. Predators are very active, and that drives the evolution of the prey to become fast as well and to become elusive.
Prior to the Cambrian, slow, small, backless creatures drifted on the current or stayed rooted to the ocean floor. How did fast, spiny fish evolve? Scientists like Long have theorized that predation drove that change, and more.
We think that predators eating prey items is something that's fundamental to the origin of vertebrates. As far as we know, speed first evolved the moment that vertebrates became vertebrates. And then vertebrates developed things like 3 sense organs, nose, eyes, ears. They evolved a heart, which gave them a circulatory supply. All this is in service of being very active.
Until now, there has been no way to see firsthand how these evolutionary changes might have taken place. Dead fish don't swim. Determined to fill in some missing pages in evolutionary history, Long hit on a plan that's straight out of science fiction. He would recreate evolution in action and be there to watch it. In a lab in upstate New York, biologist John Long is about to recreate the evolution of the backbone, 560 million years after it first appeared. Only this time, with robots.
One of the problems of the fossil record is all we have are the corpses of animals. We know nothing about their behavior. Robotic simulation is an attempt to reanimate fossils, to bring them back to life.
Long constructs robots that mimic the animals with the earliest form of backbones. One set with a variety of soft cartilage spines. Today, there are just a few species that still have backs like this. The other set has different ranges of stiffness in their spines of bone, like over 58,000 current-day species, including us. Long's plan is to see if he can discover just exactly why the bony spine spread and the equally effective flexible spine died out. The backbones appear like tails, propelling the robots through the water. In a series of trials, Long turns his fish loose to think for themselves.
We give them brains that are based on the brains that we think early fishes had. They have an onboard brain that takes input from their eyes and feeds it through their brain to a motor output. So this is a completely autonomous robot. We don't tell them what to do ahead of time. They do it on their own.
Long programs the robots to find food, here represented as light, as fast as possible, stay in the light as long as possible, and avoid predators. Like sharks or marlins, Long's robots can never stop swimming. After each set of trials, Long chooses the successful to mate, using them as the basis for the next generation's design, its evolution in a fish tank.
Now, it's not just being fast, it's also staying away from the predator, and it's also eating food. So speed is placed in the context of a complex ecology of survival.
After 10 generations of robot evolution, Long pits soft and stiff against one another, hoping to witness for the first time how the bony spine won out.
All right, Marianne, if you want to turn off the lights.
Round 1, soft spine robot.
Look, here we go. This is a very flexible tail.
Now it looks like he's going back towards the light. See if he gets back in there.
The soft-spined robot is slow but accurate. Throughout the 3-minute trial, it hugs the circle of light closely. Will the bony spine do better? Round 2, hard spine robot.
With the vertebrae in here, in the tail, looks like it overshoots the light source.
Less flexible, the stiff back has more power, but it's less accurate.
Speedy individuals tend to overshoot the food source. Sometimes speed is bad. Being fast can cost you.
If speed leads to tougher feeding, why did the soft backs largely die out? The difference shows up when Long recreates what happened in the Cambrian explosion, the introduction to the environment of predators.
The predator's job is to find the prey and try to eat it.
Round 3, soft spine robot hunt.
Ready, go. Come on, predator. Show us what you got. So what we have going on right now is the prey robot is swimming straight towards the light, but it's just detected the predator and has initiated a fast start. So it's saying, I can't eat right now, I gotta get out of the way. But now it's turning around, gonna come back into the light. Meanwhile, the predator is saying, no, you don't, I've got you. Obviously, our robots are not eating each other. That would be really expensive and kind of messy.
The soft spine is too slow to survive. And the bony spine? Round 4, bony spine robot hunt.
So this is really dramatic. Now that we have the prey with vertebrae, the predator hasn't gotten anywhere near. Man, the predator's just really overmatched here.
Even though the bony spine robot is less accurate in its movement, power and speed win out. Long's robots show that the bony spine is a powerful adaptation for survival.
Speed is really critical. And you've got to be faster than your predator.
And the essential key to speed? A bony back. The stiffer, the better.
Backbone seems like it should just be a thing that everything else is just attached to, but that's not what a backbone fundamentally is about. A backbone gives you a stiff rod that lets you be very, very strong as you move through the environment.
All the fastest fishes today have very stiff backbones. A slow wriggling eel has over 100 tiny backbones, while the speedy sailfish has just 30 larger, longer vertebrae. A stiff back is the central ingredient for speed, but it can't do it alone. Next step, add plenty of muscle.
The first time we see what we would recognize as muscle in the fossil record is in fishes. And the muscle that is inside those prehistoric fishes is fundamentally the same stuff that we have in our bodies today.
To backbones and muscles, add a biological body built for speed.
They need to have a streamlined body shape. And one of the things we find is a teardrop-shaped body evolve in the really fast fish, and also a big, wide tail.
Backbone, muscle, body shape, and powerful tail. All the ingredients came together in the sailfish, the fastest swimmer in the ocean. But not every sea creature evolved a backbone. Many thrive as successful predators using speed in a completely different way, as a weapon.
Whether or not an animal is fast isn't just limited to how it moves around in the environment. There's also how fast it can perform certain activities. An animal might be relatively slow moving around, but when it strikes at its prey, it's lightning fast.
At the same time backbones were appearing, another adaptation would begin to evolve. One that would translate speed into the most powerful knockout punch on the planet. In the dangerous world of the seas, fish developed speed to become effective predators and elusive prey. They evolved backbones, muscles, a streamlined body form, and the ability to sail through the water at sometimes astonishing speeds. But a whole other class of sea creatures never developed backbones at all. Some of them, like jellyfish, have soft exteriors and survive with minimal propulsion, mostly drifting on the current. Others, like sea slugs, can't run, but they can hide. Their defense first emerged 500 million years ago, during the Cambrian time period. While predatory fishes evolved backbones, some of their prey evolved a new and effective defense.
Around the time of the Cambrian explosion, a very important event in the history of life occurred. That was the evolution of the first hard parts. These hard parts led to the evolution of hard body coverings in a wide variety of animals.
Like a suit of armor, these hard parts, shells or exoskeletons, are protective but constraining. Shelled creatures often shuffle slowly along the seafloor. Well defended, they adapted a completely different way of getting fast to capture their prey. Like a heavyweight boxer, they might not win a sprint race, but they pack a lightning-fast punch. And pound for pound, the fastest, most powerful punch in all of nature belongs to a shrimp.
There isn't a muscle fast enough on the planet to generate the kind of speeds that we see in the mantis shrimp.
Biologist Sheila Patek studies the mantis shrimp, the owner of the fastest strike in the sea. Just 4 inches long, the mantis shrimp can shatter the glass of a fish tank and crack open crabs like they were eggshells.
They happen to like eating crabs, and it's interesting and a little bit scary to watch them eat crabs because they'll swim after them very quickly, hammer them, and they hammer them so hard that all of the legs generally pop off the crab.
Scaled up to human size, the shrimp would be a fighter with a fist that could smash through concrete. Until now, no one has ever really understood how the small but mighty shrimp could pack so much speed into its punch, and Patek was determined to find out how it worked. Patek would have to slow the punch down so she could see what was happening. She heard about a unique video system designed by NASA, powerful enough to shoot at over 5,000 frames per second, more than 100 times faster than a standard camera.
We have this video camera rolling right now, and it's continuously collecting data. It's continuously collecting images at a really high rate. What we're doing is we're waiting for the mantis shrimp to strike the snail.
Nice.
Okay.
For the first time ever, these videos allow the team to calculate the punch's speed.
With this particular species, the peacock mantis shrimp, we've recorded speeds of over 19 meters per second, which is 50 miles an hour. On top of this, they're accelerating at over 100,000 times the force of gravity.
The punch's speed is 2 times faster than scientists had imagined, with the acceleration of a bullet from a gun. Protect knew that no muscle on the planet can move this fast, and yet, pictures don't lie. Carefully analyzing each frame of the video, Patek pieced together the shrimp's secret weapon, its shell.
Mantis shrimp have a big, slow muscle that they slowly contract, store up all kinds of elastic energy in the system, and then when they're ready to strike, they release a little latch, and then the limb flies out at extremely high speeds.
In engineering, the design principle of elastic energy gets used in crossbows, catapults, and the full-throttle explosiveness of a fighter jet jumping off a carrier deck when the restraining hook is released. Like loading a catapult, the shrimp slowly peels its arm back, storing energy by compressing muscles in several spots, including a specialized saddle-shaped structure within the shell. A latch holds the arm in place. When the latch is tripped, the compressed shell snaps back to its original shape, propelling the punch forward with lethal speed. Instead of limiting its speed, shells give these creatures a strike too fast to be seen.
One could imagine, over evolutionary time, that this appendage was able to become faster and faster, especially because of the origin of this latch mechanism. Once this mechanism evolved and became sort of a key characteristic in this group, this allowed them to diversify into a number of different niches.
Other invertebrates use the same catapult mechanism, from the smashing speed of an ant's trap jaw to the springy strength of a grasshopper's knees. But even the enormous speed of the shrimp's punch couldn't account for its glass-shattering power. Patek knew there was more to the story and found it in the soundtrack.
Oh, nice. Okay.
All
so
right.
let's take a closer look. So you can see that there are two peaks of sound. So there's a burst of noise here and then a second one. And they're about 4/10,000th of a second apart, so half a millisecond apart.
The second hit, Patek realized, must have been created by an exploding air bubble, a powerful byproduct of speed known as a cavitation bubble. Cavitation bubbles appear when objects like boat propellers vaporize the water surrounding it, creating bubbles loaded with intensely compressed energy. When the bubbles burst, the energy is suddenly released, creating shock waves strong enough to damage steel. It's a 1-2 punch, and it gives the shrimp a guaranteed knockout.
They generate thousands of times their body mass in peak force, and that's what's really impressive. They're fast, they have high accelerations, but their force is pretty much unmatched.
From a faster swim to a deadlier strike, both vertebrates and invertebrates evolved to use speed to stay one step ahead of the competition. While predation made the seas a brutal and dangerous world, 350 million years ago, the land was brimming with opportunity.
Living on land brought a whole suite of new physical challenges to the earliest tetrapods. Living on land required dealing differently with gravity, whereas water is much more buoyant. Gravity is much more of a major force on land.
The first fish to push their way onto the muddy earth are strange four-limbed creatures called tetrapods. They were slow, but a single change in their body design would lead to the speed of the cheetah, racehorses, and every fast animal on land today. How did these ancestors of amphibians, reptiles, birds, and mammals adapt their fishy bodies to fight gravity?
About 300 million years ago, these guys crawled out on land, and they really haven't changed all that much since.
Biologist Stephen Riley studies the Pacific giant salamander. An amphibian, it's the closest living relative to the original tetrapods.
This animal is as good as an example of the first four-legged animals to go out on land. It has this sprawling posture.
The salamander's legs have to function both in water and on land. They are placed to the side of the body. In water, they function like the paddles on a boat, but they are still able to push along on land. Like many compromises, it's an imperfect system, as Riley demonstrates.
This instrument that we've built will measure the animal pushing on the ground up and down, and forwards and backwards, and also side to side. And you can see he's kind of a slowpoke, and he doesn't like to walk very far. Okay, buddy.
Riley's track collects force data as the animal walks across. The data shows that the walk is wildly inefficient. The splayed limbs of the salamander move it up and down more than forward. This system is enough for an amphibian that only spends a portion of its life on land. Animals living on land full-time would need a better system or die from an inability to catch prey and escape from predators.
There he goes. Beautiful.
One of the first land-dwelling animals to evolve from the amphibians were reptiles, like the Schneider skink.
One of the mysteries we're trying to understand is how did these animals change to become a very fast-running animal like a lizard?
To see exactly what changes between the slow salamander and the fast lizard, Riley combines his force data with high-speed video. The footage shows the key transformation, from paddles on a boat to rubber on the road.
Salamanders always put their feet in the same place relative to their body as they're walking. They don't bring their legs underneath them. Whereas lizards have been shown that as they go faster, they bring their legs underneath their body.
Underneath their bodies, the reptile's legs can move them forward without having to lift them up and down. The reptile's adaptation to life on land was an evolutionary landmark. From those first running reptiles 280 million years ago to thoroughbred racehorses today, every fast-moving land animal takes advantage of the same basic body structure.
One of the things that all the fast animals have in common is that the limbs have been moved under the body. So if you look at a horse or a cheetah or a dog, you'll notice that their limbs are moved underneath the body so they can swing underneath and the body can travel on top of them.
Fast and deadly, reptiles grew to dominate life on Earth. Their cousins, the dinosaurs, grew to enormous size, so large that some stood up and had to find new ways to run on 2 feet or die. The fastest animals on land all run on legs directly underneath their bodies, on 4 legs or on 2 legs. Bipedal creatures first emerged nearly 290 million years ago, and they were small. But their descendants, the dinosaurs, grew large. At 12 feet tall and carrying 6 tons, how could the largest bipedal meat-eater of all time, T-Rex, hunt down any game at all?
It's an important question how fast dinosaurs grow. Were these slow-moving, lumbering lizards, or were they fleet-footed animals that were charging across the plains?
Bill Sellers is a computational biologist who usually studies speed in early primates. But recently, he turned his attention to the mystery of the biggest predator of all time, T-Rex.
T-Rex is an absolutely fascinating dinosaur. It's very strange. It's got these silly little forelimbs, and it's got these hugely long hind limbs. And that's why some people have interpreted it as a very fast-running animal. And we really wanted to know whether this was true or not.
Sellers realized that if he could determine T-Rex's speed, he could solve one of the central mysteries surrounding T-Rex.
There's been this ongoing argument about whether T-Rex was a scavenger or whether it was a pursuit hunter. Obviously, if T-Rex was a scavenger, it would just simply need to be able to arrive at a conveniently dead dinosaur and be large enough and scary enough to chase off the other scavengers. But of course, if it was actually a predator, it would need to be able to hunt down and capture its prey. And to do that, it would have to be fast.
If he could prove that T-Rex was fast, he could support its role as a fierce hunter. But how to do it?
We can't make engineered models that accurately represent the biology. So what happens if you look at a robot, they're very clever, but they tend to be much, much heavier than the equivalent living animal. And also, muscle does not contract in the same way that little electric motors or hydraulic systems work. So we can't use physical models to estimate performance.
Power on.
Taking a page from Hollywood, Sellers is attempting to build a computer model of T-Rex. To do what's never been done before, this virtual model will have to be the most accurate rendering to date. How do you outdo the monsters of the silver screen? Start with the LiDAR, the most accurate remote sensing system in the world, developed for the US government to create detailed maps of the ocean floor. Sellers figured he could use it to map the inner landscape of T-Rex.
What it's got is a laser, and the laser actually shines out, and it's what's known as a time-of-flight system. So you actually measure the time that light takes to get from the unit to wherever it's shining at and back again. That will give you a measure of distance. And the advantage of this is instead of having to go around by hand and draw the animal or use a handheld laser scanner, we can just use this one piece of equipment and put it in several different locations around the building, and it'll take a full 3D scan of the whole animal. But we do need more detail in certain areas.
The LiDAR allows precise calculations of bone dimensions, but Sellers needs more. He needs to know how and where the muscles attach to the bones. He starts with the foot bones critical for running.
Particularly this area of the bone here, this is a little bump where one of the muscles attaches. And it's details like this that are very important when we're trying to reconstruct the musculature of the animal.
Sellers scans in bones and muscle attachment points by hand, each in painstaking detail. He then uses software he designed to put the pieces together. The final step is to teach the finished model how to walk. He's already done it with one of T-Rex's favorite meals.
Now, this is a hadrosaur. This is what we think that T-Rex probably ate. And we don't make the animal move in a particular fashion. We just tell the computer, given the musculoskeletal system that you've got, just make this creature go as fast as possible. It's going about 10 meters per second.
10 meters per second translates to a top speed of 22 miles per hour. Could T-Rex catch it? Sellers believes he is on the verge of settling the debate. First, he races his preliminary T-Rex model against some familiar runners to make sure his model is functioning properly.
So T-Rex at the far side, and then we've got 3 living bipeds that we can compare them with. This is modern human, this is an ostrich, and this is an emu. And as you can see here, there's some very small dinosaurs that we think are very quick, but basically the ostrich here is faster than all the bigger dinosaurs. And the T-Rex is the slowest, but it's still faster than the modern human.
The modern human can run a mile in under 4 minutes. That's 15 miles per hour. And the clock on T-Rex?
What we found out about T-Rex was that it is a relatively fast animal. It goes at about 8 meters per second, so that's about 18 miles per hour.
At 18 miles an hour, T-Rex could clearly run down the fastest man alive over a quarter mile. But what about the hadrosaur? With a top speed of 22 miles per hour, it could outrun T-Rex, which Sellers says is just right.
T-Rex is just running for dinner, basically, whereas obviously a hadrosaur is running for its life, and you would expect it to put that much more effort into being faster.
It seems paradoxical, but most prey can outrun their predators at top speed. Cheetahs are an exception. If prey can't outrun predator, it will be shortly extinct.
You wouldn't catch a healthy hadrosaur. You would tend to pick out the elderly or the injured, the ones that were going slightly slower than the rest, and those are the ones that you would be able to catch.
A balance of speed between predator and prey allows for the survival of both over time.
There's a constant arms race between predators and prey. And speed presumably evolved so that prey could escape from potential predators and so predators could catch their prey. There's a continual cycling of events such that the prey becomes faster, the predator becomes faster, with the result that in some lineages, speed has reached enormous proportions.
For T-Rex and the cheetah, a combination of factors including muscle power and body design allowed them to attain frightening speeds. Today, horses race faster than ever before, the result of centuries of human-controlled breeding. It's a long-term experiment in human-directed evolution on fast forward, and it's only the beginning of what may be to come. There's a human fascination with speed. Watching horses run has been a human pastime for at least 1,000 years. Horse-like creatures first emerged about 52 million years ago. They were slow. As they evolved, their descendants ventured from wooded areas onto open plains to graze. The ones fast enough to escape predators on short notice survived.
If needed, they could run away from their predators rapidly, but they were not designed by natural selection for high speed over any significant distance. They were designed for walking and trotting a much lower speed over a much greater distance.
Dr. Ben Martin is a veterinarian and professor at the University of Pennsylvania. While horses have been bred through selective mating by humans as far back as the 1300s, Martin sees a disturbing new trend in the practice, creating horses that are faster than ever, but increasingly fragile.
Those three across the track. You have horses that are now breeding stallions that have raced fewer and fewer races. They've run at faster speeds. They've been more successful racehorses for a shorter period of time. You take their genes and put it into the pool, and what happens is you're selecting for horses that have more and more speed, but less and less soundness and less stamina.
Champion thoroughbreds now top 50 miles an hour and break down more than ever.
Natural selection operates on the whole body and everything that the body does. When we select for animals that can run fast, all we think about is speed. And so racehorses, for example, are so fast that they actually can injure themselves by going as fast as they do.
Like many fast mammals, including the cheetah, the horse concentrates muscle power in his back with very little weight in the legs. This extreme combination allows the animal's massive back muscles to move its ultralight limbs at incredible speed. But Martin believes that human-controlled breeding has created an animal that is dangerously out of balance.
When a horse gallops, he pushes off his hind end, and then he lands with a front foot, and then the last foot that he lands on is called his lead leg. That's the leg that suffers the most pressure. That's the leg that is most likely to be injured at high speeds.
Martin has seen hundreds of speed-induced fractures that have forced owners to euthanize their racehorses.
You're asking these horses to do the maximum that they can do. Your heart is in your throat the whole time, and you're just hoping your horse is going to finish the race sound.
And the Daybait forges to the front.
As far as I'm concerned, the thoroughbred probably is right at the edge of how fast he can go and how long he can go.
Horses first evolved speed to escape predators on open plains. Scientists now believe that the key to the success of early human beings was not speed, but endurance.
One of the theories is that as we came out of the trees, we started chasing after animals to feed on or jogging between the carcasses that we found to feed upon. And both of those require long-distance running. And so as a result, we became very good at running long distances. When you look at the human body, you can find different parts of it that seem to fit this story that were built for running. For example, we have long legs, so we take big, long strides. We run bipedally very efficiently. We have springs built into our tendons in our legs so that every time we take a step, we get some of that energy back. And another thing that looks like it's built for running is our skin. We've gotten rid of a lot of the hair. We've got sweat glands all over our bodies.
Our ability to stay cool by sweating meant we could outlast fur-covered beasts that would overheat in a prolonged chase.
A lot of the animals that run a lot faster than we do are actually slower over very long distances. And a good endurance human runner can wear them down over time, catch them, kill them, and eat them.
Today, humanity is poised on the brink of new breakthroughs in speed, as the full weight of scientific analysis is brought to bear on training sprinters.
bottom line on everything is that human speed comes down to two things: hitting hard and hitting fast.
Peter Weyand studies the physiology and biomechanics of speed. He's trying to figure out how humans can be trained to run faster.
We'd like to compare the mechanics of running at a slower speed with a fast speed, and what we want to see is how those mechanics change.
Weyand's subject today is Jason Powell, a professional sprinter with world-class speed. To find out how Jason's body moves so fast, Weyand has modified a treadmill to record each time Jason's feet hit the ground.
So Jason, whenever you're ready. Looking good, Jason, looking good. If you look at simply the duration of each one of these spikes, how spread out it is, we know exactly how long his foot is down.
Some simple calculations reveal that Jason takes almost half a second to move his leg back to a starting position after each step. Data that comes as a surprise, because even casual runners move their feet just as fast.
You might suppose that faster runners simply move their limbs faster. They hit faster stride frequencies. So we tested subjects that were very fast sprinters, so-so, and slow. And what we found was the slowest person we tested, who could run at about 12 or 13 miles an hour at a top speed, she was able to pick her foot up off the treadmill, put it back down in front of her, just as quickly as the fastest sprinters in the world.
Leg repositioning time doesn't affect a runner's overall speed. So what could the difference be? Weyand began to check the treadmill's other readings, looking for any variance between slow runners and fast. He found that the key wasn't speed, but strength.
One of the things that we found is that what's critically important for hitting these very high-end speeds that the elite sprinters hit is that they have to be able to hit the ground very hard in relation to their body mass. So the fastest sprinters will hit the ground with forces that are 4 to 5 times their body weight. Look good, Jason, look good.
Using their large quadriceps to literally pound the pavement, the fastest runners launch themselves into the air. They spend significantly less time with their feet on the ground than slower runners. The harder they hit, the faster they go. So while the racehorse and the cheetah pack their power into their backs and have little to no muscle on their legs, humans use their backs to stand upright. Muscular legs evolved to generate running power. But the more muscle, the more weight, and the more weight, the more drag to slow the runner down. Where's the tipping point where humans just can't get any faster? Scientists believe it may soon be here.
There seems to be a limit to how fast humans can run. Although the record time for the 100-meter dash has been going down and down and down, the amount that it goes down is smaller and smaller and smaller over the time, and it's very unlikely that it's going to drop in half ever.
But Peter Weyand is not so sure.
Well, we know what matters for going fast mechanically, what the muscles in the limb have to do, and it's intrinsically speculative for us to say the ultimate limits for how well this can be done. We know that the biological materials that nature provides certainly can confer speeds much faster than humans go. But where those outer limits are, we have no way of assessing.
Yet Weyand believes that even if there is a limit to speed, we may have found a way to cross it. As humankind begins to apply technology to our own bodies, in effect directing our own evolution, the old limits may not apply.
If we think about the future of human speed and athletic competition, we are in some respects on the cusp of a brave new world, because advances in technological design, whether it's shoes, tracks, artificial limbs, or genetic design, we're at a point where we're beginning to be able to control the properties of the tissues in our own body. And that's a stepping off point where it's very difficult to project where the end is going to be.
Will we create a race of super athletes for our entertainment and inspiration? Or will unchecked technology lead to disaster for our future? For 1 billion years, many animals have evolved to become faster and faster. And with humans now poised to fast forward the process, it's clear that by means both natural and man-made, speed will continue to evolve.